And we have 1 minute for any final questions you might have. Nothing. Okay. All right, I'll just wait till my clock says 8:20. Someone else is recording too. Yeah, okay. Right. So Ahsan, we'll take that after the class, okay? Now, and Manish, your question too is maybe after the class. Let me start with today's class. So we're going to continue our series on training neural networks. Specifically, we'll talk about using gradient descent to train networks. Now, here's where we ended up in the last class, right? We saw how to set up the problem of training a network to model a given function. We are given input-output pairs from our target function. We define a divergence function, which is which quantifies somehow the difference between the actual output of the network and the desired output of the network in response to a given input. Because divergence has the property that when the actual output is not the same as the given output, desired output, it is positive, otherwise it's 0. We compute the average divergence over all of our training samples. And because our training samples are given, the only thing that you can change to change this average divergence are the parameters of the network. This is what we call our loss. And we train the network to minimize this loss. This loss is the empirical risk over drawn samples. We train the network to minimize this loss And we hope that in doing so, you'll end up with a pretty good estimate of the actual function itself. Now, this task over here, minimizing the loss, is an instance of function minimization. This loss is a function of the network parameters. We are trying to minimize this loss with respect to the parameters. So it's one instance of minimizing a function with respect to its argument. So we'll begin, before we continue with our discussion on neural networks, with an initial discussion on function optimization, with an initial brief note on derivatives. Okay. So before I begin, can anybody tell me what you understand by the term derivative? Anyone? What is the derivative?
Slope of the function at a given point.
It's a slope. Okay. The slope is a good one. The rate of change of a function, change in one variable with respect to another, all of these are good answers, right? But formulaically, how do you define it? Mathematically, how would you define it? All of these are correct answers, right? Or almost all of it. Yeah, go ahead.
As a limit.
As a limit. So limit, fine. Limit as a small perturbation goes to 0. Good answer. But then I was all correct. So maybe I won't stay with that. But then here is what we really mean by derivative. It's a limiting case of something, but a derivative of a function at any point tells us how much a minute increment to the argument of the function will increase the incremental value of the function. So Karthik, can you turn your mic off? So this is basically what a derivative is. But then we have in school, how did you write derivatives? If I had some function y equals f of x, you have to forgive my scroll, you wrote things as dy over dx, right? This was how you defined your derivatives in school. But here is the actual and only correct definition of a derivative, which is delta y, which is the increment in y, delta x is the increment in x, and the derivative is the multiplicative factor that multiplies the increment in x to give you the corresponding increment in y. That is the only correct way of uh, defining a derivative. What is the multiplicative factor by which I must multiply delta x to get delta y? Now, that doesn't mean this is wrong, and yet I claim this is wrong. Where would this be wrong, this notation? Anyone?
Vectors.
Vectors, right? You cannot write this for vectors. There's no such thing as dividing by a vector or even a matrix, right? So this is the only correct definition for a derivative. But then let's look at special cases, specific cases. For a scalar function of a scalar variable, so you have y equals f of x is a scalar, y is a scalar. So you're going to get a function of this kind. Then the derivative over here of the scale of the function. Wait a minute, let me turn off my ceiling fan. It's making a squeaky noise. The derivative of the function over here is going to be a scalar value by which you multiply this delta x, because x is a scalar, delta x is also going to be a scalar, and it's going to give you the corresponding increment in y. And in this particular case, this notion, the notation of dy over dx is appropriate, but a more reasonable notation is going to be, if y equals f of x, f prime of x is a more reasonable notation. Why is that? Anyone? Notation wise? Why would this be more reasonable?
Because it shows the derivative is a function of x.
It shows that the derivative is a function of x. This notation hides it, right? Now, what exactly does the derivative at any point show? The derivative is actually the rate of change of the function at that point, basically the slope of the function. So if increasing x increases f of x, like in these regions, then the derivative will be positive. If increasing x decreases f of x, like over here, the derivative is negative. In both cases, if the function is steep, then the derivative will be large in magnitude. If the function is shallow, the derivative is going to be small in magnitude. So here it's going to be large, here the function is shallow, it's going to be small. And if the function is just locally flat, like in these regions, it's not increasing or decreasing, then the derivative will be 0. Now, consider a scalar function of a vector x. So this was a scalar function of a scalar. Y is a scalar and x is a scalar, right? Now, let's consider y equals f of x, where x is now a vector. So it's a vector of this form with many components x1 through xd. In this case, how would we define the derivative of this function at any given x? In that case too, this is the only true definition. Delta y equals alpha delta x is the only way of defining the derivative. And now, if I have y equals f of x, and if I have y equals f of x, and x is x1 through xd, right? Y is a scalar, x is a vector, okay? What is delta y going to be? Is delta y a scalar or a vector? Anyone? Delta y is going to be a vector?
Scalar.
Y is a scalar, so delta y is going to be a scalar, right? What about delta x?
Vector.
What is it, and what is the dimension?
D.
D. It's going to be delta x1 through delta xt, correct? By definition. So if I say delta y equals alpha delta x, what can you tell me about the shape of alpha?
That will be a row vector.
It has to be a row vector. It has to be a row vector, right? Because I have delta x1 through delta xt. And so I need this guy to be alpha 1 through alpha d. And this is going to be delta y, right? So the derivative of y with respect to x is going to be a row vector. Now, if I expand this out, this is going to be alpha 1 delta x1 plus alpha 2 delta x2 and so on, correct? Now, delta x is something that you can choose. It's up to you. You're saying for a small increment, what is the corresponding in x, what is the corresponding increment in y? So I could very well choose delta x to be of this form, where delta x equals, only the first component is incremented and the rest are not incremented. In this case, what is delta y? Anyone?
Alpha
delta
1,
x1.
delta x1.
It's just going to be alpha 1 delta x1, right? So in this case, alpha 1 is what we will call the partial derivative of y with respect to x1, which tells you how much y will increment when only x1 is incremented and the rest are not incremented. You've all heard the term partial derivatives, of course, right? And so delta y is going to be the partial derivative of x1 times delta x1 plus the partial derivative of x2 times delta x2, and so on. So this is how it's going to be. Then what is the shape? What is alpha going to be? What is the vector? What is the derivative alpha going to be? What's this going to be? We agreed that it's a row vector. What are the components? Anyone?
Partial derivatives.
Partial derivative, right?
Delta y upon delta x1, then delta x2, then delta x3, so on.
And these are the partial derivatives. These are all scalars, so I can write the d over d format, correct? I mean, it's not quite precise, but yeah, you can write that format. So I can write, so this is what I can say when I'm speaking of a multivariate scalar function. If I'm using, I will typically use this derivative notation. I'm going to say delta y is this derivative times delta x, but a common notation is to use this inverted triangle of y with respect to x. It says that this is the derivative of y with respect to x, and this derivative is this row vector of partial derivatives. But then you guys have almost all certainly heard of the term gradient. What was the gradient? Do you remember? Anyone? What is the gradient?
It's the same thing, but as a column vector.
Yes, the gradient is the derivative transposed. The gradient is the transpose of the derivative. And now here is a general rule that we're going to keep encountering later in the course, that if I have a scalar function of some object over here, which could be a vector or a matrix or a tensor, then the derivative of y with respect to, let me call this x, is going to have the same shape as x transpose. This is always going to hold. And you can see that over here, right? And so the transpose of the derivative is the gradient. But then what exactly does the gradient stand for? What is the gradient? Let's look at this again. Now, if I have a function f of x of, f is it's a scalar function of a vector, then I can write df of x is this derivative f of x times dx. This is just what we saw. The derivative is just a row vector of partial derivatives. The gradient is the transpose of the derivative. Can anybody tell me what, in the case of the scalar function, the derivative gave us the rate of change of the function, right? In the case of a vector, what does this gradient stand for? Does anybody know? What does the gradient stand? Pardon me?
The direction of the change, or the steepest change.
The direction of the steepest change, and we can see why this is the case, right? This is a vector in a product, right? This is a vector in a product. And so to understand its behavior, let's consider a well-known property of inner products. Suppose I have two vectors u and v, okay? The inner product between u and v is magnitude of u times magnitude of v times cos theta, which is theta is the angle between the vectors. So if I fix u and I keep rotating v, this is the inner product as the angle between the two changes. And you will find that the inner product is maximum when the two are perfectly aligned, because at that point, theta is going to be 0, right? So this is a well-known property that the inner product between two vectors is maximum when the two are perfectly aligned. And so when you go to the gradient, again, the gradient at any function of a function at any point is given. The gradient is a property of the function. What you can change is this incremental step dx. And so if this red line shows the gradient and the blue arrow shows the direction in which you're walking, as you change the direction in which you're walking, you can see that the increment in the function keeps changing, and the function increases maximally when the step you take is in the same direction as the gradient. In other words, the gradient is the fast direction of the fastest increase in f of x. Is this clear to everyone? Right. Any questions? Somebody say yes so I can keep moving.
Yeah.
All right, one person said yes. Okay. So the gradient of a function is the direction of the steepest change of the function. So, and again, remember the gradient is a vector of partial derivatives. It has a direction and it has a length. So moving in the direction of the gradient, there are many directions in which you can walk. For example, over here, if you walked in this direction, then the function would increase. If you walked in this direction, the function would increase. There are many directions in which the function can increase, but the gradient is the direction in which the function is going to increase the fastest. If you want to walk in a direction where the function decreases fastest, which direction would you walk in?
Opposite.
Anyone? Exact
Opposite.
opposite, right? You're going to walk in the negative gradient. You're going to walk opposite the gradient to decrease the function fastest. Now, the gradient also has, and of course, at local minima and local maxima, the function is locally flat, so the gradient there is going to be 0. Over there, there is no direction in which you can walk where the function will increase. The gradient has another property, which is that we will use. If you slice the function vertically, right, at any height, then you will get an edge. The value of the function is going to be constant all along this edge. The corresponding values of x, where the function value is constant, is called a level set. And the gradient is always going to be perpendicular to the level set or the level curve. So this is something that we use. And just as a by the way, you can also compute the second derivative of a function of a vector with respect to its argument. This is called the Hessian. It will be a matrix where the ijth component of the matrix is the partial derivative of the function with respect to both the ith component of x and the jth component of x. Now, I'm not going to spend too much time on the Hessian, except that to state that this matrix is going to be positive definite at minima. If you don't know what the term means, don't worry. We'll revisit it. It means that no matter what direction you walk in, the second derivative of the function will be positive. It doesn't matter which direction you're looking, along that direction, the second derivative will be positive. So at this point, we have a quiz. You have 45 seconds for this quiz. Are you guys seeing the quiz? Yeah. It's 10 seconds, guys. Most of you are not responding. All right, let me stop the polling. This is kind of disappointing. Only 2/3 of you responded. But anyway, this first one is true. At any location, there are many directions in which you can step such that f of x increases, right? The direction of the gradient is the direction in which the function increases fastest, but the gradient is not the derivative of f of x. It is the transpose of the derivative of f of x. So this third one is wrong. Now, if y equals f of x is a scalar function of a 1 cross n vector, then the derivative is going to be of an n cross 1 vector, then the derivative is going to be 1 cross n, because the derivative is a transpose of the argument. Okay, so let's move on. Let's return to the general problem of optimization. We are given a function f of x, and we want with respect to some variable x. X could be a scalar, like in this case. It could be a vector, like in this case. Our problem in optimization is to find the location value of x where the function is minimum. Now, you probably already tackled this problem in school. So I'm going to have another poll right here to help you recall how we did this in school. Can I? Yeah. So there's a little quick poll. Answer this, be quick. You have 30 seconds. Five seconds, guys. All right, let me stop. So obviously, most of you know the answer. The derivative must be 0, and the second derivative must be positive. Let's see why. Okay, for a function of a scalar, at the minimum, the function is typically going to be flat, so the derivative is 0. Now, being a minimum means that the function is greater everywhere around this point. So it doesn't matter whether you walk from this direction or you come from this direction, the function will initially decrease and then it will begin to increase. So the minimum is what is called a turning point. To identify the minimum, you have to find values, the turning points, the values of x at which the derivative is 0. But then both maxima and minima are turning points. In the case of maxima, the function initially increases, then it becomes flat and then decreases. In the case of a minimum, the function initially decreases, becomes flat, and then increases. So if you consider the slope of the function, before the maximum, the slope is positive because it's increasing. After the maximum, the slope is negative because it's decreasing. If you consider a minimum, before the minimum, the slope is negative because the function is decreasing. After the minimum, the slope is positive because the function is increasing. So if you consider the slope of the slope, the second derivative, it's going to be negative at minima, at maxima, and at minima, it's going to be positive. And so the standard check that you had, what you learned in school to find the value at which a function was a minimum, you first solved for the x at which the derivative was 0. That meant you found a turning point. Then you check the second derivative. If it was positive, it was a minimum. Otherwise, it was a maximum, right? Now, not all locations where the derivative is 0 are turning points. Consider this function, right? The derivative is 0 over here. The derivative of the function is flat here, so the derivative is 0 here as well. And the derivative is 0 here. This is a maximum. This is a minimum. But here, what happened was that the function initially decreased, then slowed down and flattened, and then continued to decrease. And so this is what is called an inflection point. If you plot the derivatives of this function, the derivative is going to be 0 here. It's also going to be 0 at the minimum. It's also going to be 0 at the inflection point. But at the inflection point, something strange happens. In the case of the maxima or the minima, the derivative crosses 0. In the case of the inflection point, the derivative is initially negative over here. So in this case, you had a function of this kind. The function was decreasing and then flattened and then decreased. So the derivative was negative. Let me change let's get a different color. So the derivative was, negative, and then became 0. And then it went back to being negative because the derivative slope here and here are both negative. But suppose I had a function of this kind. What is the of this kind? It increased, flattened, and increased. What is the shape of the derivative going to be like? Anyone? What's it going to be like? Paraboloid. It's going to be something of this kind, correct? So the point is that just finding a location where the derivative is 0 doesn't tell you anything. And even if you look at the second derivative, here for the maximum, the second derivative is going to be negative. For the minimum, the second derivative is going to be positive. At an inflection point, the second derivative is actually going to be 0. So these situations can get very complex. Now, what about for functions of multiple variables? For functions of multiple variables, the minima are still turning points. But first, quick recap, let's see what you remember of the derivatives of multivariate functions. We just covered this. You have 30 seconds, guys. Wait, no, I think I'm giving you the same quizzes before. I made a mistake. That's okay. I was planning on giving you, wait. Doesn't matter. So yes, someone points out that this is the same quiz as before, but the direction of the gradient is the direction in which the function increases fastest. Some mix up. Let's ignore that. But anyway, the point about this location, right? The minimum of a multivariate function is that it's a minimum. So it doesn't matter which direction you approach it from, whether you come this way or whether you go this way, the function will initially decrease and then continue and then increase, both for minima of this kind and for minima of this kind. And so to find a minimum or any turning point, we must find a point where shifting in any direction by a microscopic amount will not change the value of the function, and shifting by a little more than a microscopic amount will increase the value of the function because the derivative is 0 at the minimum, right? So the minimum, even for a multivariate function, is going to be a turning point. The gradient is going to be 0. And so to find the minimum for a multivariate function, what we will do is to solve for this, for where the derivative is of the gradient equals 0. This will find turning points. Then to find out if it's a minimum or a maximum, we compute the Hessian matrix, and we compute the Hessian at these candidate solutions. If the Hessian is positive definite, meaning all the eigenvalues are positive, then it's a local minimum. If it's a negative definite Hessian, it's a local maximum. Otherwise, you really can't say anything about that point. All of this is very fine. This is what we learned in school, or maybe a little more than that. But the fact is that it's often just not possible to simply solve for the gradient of x equals 0. Because this gradient may not have a nice closed form, or even if it does, this equation might not have a nice closed solution. In this case, we're going to use an iterative procedure. We will begin with a guess for the optimal x, and then iteratively refine it until the correct value is obtained. So in the iterative procedure, we'll start with an initial guess x0, and then we're going to check if this location is actually a minimum. If it's not a minimum, then we update the estimate to a new location and check again. And if that's not the minimum, we update it again. And we keep doing it until we find a point where we have some reason to believe we are at a minimum, that the function no longer decreases. Now, this is the same for both univariate and multivariate cases. There are a couple of things to resolve here first. If this is not a minimum, which direction do I step in? And how large must this step be? In a greedy sense, we want each step to decrease the function. So we will start with our initial estimate. Then from that initial estimate, we're going to check which direction to move in to decrease the function. That information is going to be available in the derivative. Now consider a function of a scalar variable. If the derivative at any point is negative, it means the slope is negative, right? That means if you increase x, the function is going to decrease. So if your initial estimate is out here and that you find that the derivative there is negative, then you want to shift your estimate forward. You want to adjust it forward. On the other hand, if you're at this location, the derivative is positive, the slope is positive. So increasing x a little bit will increase the function, whereas what you want to do is to find a minimum. So you want to go backwards. So when the derivative is positive, you're going to push the value, your estimate, backwards in the other direction. And so this gives us this approach of gradient descent. I'll tell you why it's called gradient descent in a bit, but then this is a very trivial solution. You're going to initialize your estimate for the optimum. Then at that location, you're going to check the sign of the derivative. If the derivative is positive this way, then you want to step back. So you're going to subtract a step. You're going to shift backwards from that estimate. If the derivative is negative, you're going to take a step forward. You're going to add a step to that x. Now, what is the step size? We won't get into that just yet. Now, I can simplify these two, this if clause based algorithm into something simpler. I can just say that the updated value is going to be this xk plus 1, which is the k plus 1th estimate, is xk minus the sign of the derivative times step. Now see what happens over here. If the derivative is positive, the sign of the derivative is positive. So I'm going to subtract a step, I'll be going backwards. If the derivative is negative, the sign of the derivative is negative, minus and minus become plus. So I will be adding a step and I'm going to be going forward. So this algorithm is identical to this guy. Now I can simplify this even more. Instead of multiplying the step by the sign of the derivative, I can just say, forget about getting rid of the sign. I'll just use the derivative as is. And so I can just say that my k plus 1 estimate is the kth estimate minus some step size times the derivative itself. Again, observe that if the derivative is positive, this will cause x to shift backwards. If the derivative is negative, this is going to negative and negative become positive. This is going to cause x to move forward. Now, directly using the derivative in this manner rather than just the sign has a very nice property. So typically, you like functions to be of this kind. If your function is of this kind, when you're far away from the minimum, the derivative will be steep. When the derivative is steep, you can know that you're far away from the minimum, you can take a giant step because the magnitude of the derivative will be large. Then as you get closer to the minimum, you want to get careful and you want to take smaller and smaller steps. And when you have an algorithm of this kind, because the step itself depends on the length of the derivative, it naturally behaves very nicely in this manner in functions of this kind. So this is actually a very cool way of looking of incrementing, updating your estimate. And so when you have now that's for a scalar function, right? For a multivariate function, the same situation stands. Remember that in a multivariate function, the gradient is the direction of the fastest increase. The negative of the gradient is the direction of the fastest decrease. And so we're going to say, if you want to find the maximum of a function, you're going to try to maximize the function as fast as possible. You're going to go in the direction of the gradient. If you want to minimize a function, you're going to go against the direction of the gradient. And so because in our case, we're trying to minimize the function, you're always going against the gradient, direction of the gradient. You are walking down the gradient. So this approach is called gradient descent. Now, so you can keep updating your estimates. When you stop, you can stop either when additional updates don't decrease the function anymore, or when you find that the slope has actually become 0. So, which means that you can test for whether the function value has not changed between subsequent iterations, or if the gradient itself has become very small. So here's the overall gradient descent algorithm. You're going to initialize your variable. Then you're going to iteratively compute the gradient of the function at the current estimate, and you're going to update the estimate in the direction opposite to the gradient. You're going to step against the gradient, and you will keep doing this until the function doesn't change anymore. Now, so you cannot. You can only know that the function is not changing anymore. You have no way of knowing whether it's a local or a global minimum. And of course, the step size can be changed. We're going to see a lot more of that in a couple of classes. Now, for nice bowl-shaped functions of this kind, gradient descent is guaranteed to find you the minimum. For functions of this kind, you could end up at a local minimum. You could end up at inflection points. You could end up at global minima. You have no guarantee. All that you know is that you're going to end up at one of these locations. Now, I'm going to try releasing pole 4. So here is your next pole. Now, you have 30 seconds, guys. Five seconds, fellows. Okay, let me stop. But again, the way, if you want to decrease the function, the direction in which you want to move is exactly opposite to the direction gradient of f of x. So this is basically what we've seen so far. And so, having briefly reviewed gradient descent, let's return to our problem, training neural networks. Here's our problem stated again. We are given a collection of a training set of input-output pairs. Each training instance includes the input to the network and the desired output, the value that you want the output to be. We define a divergence between the actual output of the network and the desired output. The loss, we define this loss function, which is the average divergence over all of your training samples. We're going to minimize this loss with respect to W. Now, the network is a complicated function, so the loss is also a very complicated function of the parameters. So we're going to use gradient descent to minimize it. This is our overall gradient descent algorithm. W, again, the loss is a function of the parameters, which I've represented as W. So you would initialize the parameters and then iteratively keep adjusting the parameters in the direction opposite to the gradient of the loss with respect to the parameters until the loss doesn't change very much anymore. So let's sort of see how we would implement this. But before we proceed, we actually have to specify the loss function that we are minimizing fully. We want to minimize this loss. Now, to minimize this loss, we have to define every component of the loss fully. What are these input-output pairs? How do we represent them? These are I haven't clarified. What is this function f? What is it exactly? And what are its parameters? And third, what is the form of this divergence function? We have to specify all of these. Without that, we cannot specify the loss. So let's start with this first. This is the simplest question because we've been talking about it for a while, and it's also at the core of the problem. What is this function f? Our f is a neural network. It's a multi-layer perceptron. We are going to assume that the network is directed. So that what that means is that when an input comes in, each layer of neurons processes the input and passes it on to the next layer, and the flow is strictly directional from left to right. There are no loops. Once a neuron processes an input, the input doesn't go back to the neuron. We're going to assume that the network is layered. A layer is a set of neurons that are all at the same depth with respect to the input. We already saw this in the class. So each layer of neurons only gets inputs from the previous layers, and the output of each layer only goes down to subsequent layers. There's some terminology over here. The input is often referred to as an input layer. This is kind of an unfortunate terminology because it causes some people to imagine that there are actually neurons over here. It's called an input layer just because everything is called a layer, but the input is not a layer. There are no neurons over here. The input layer simply refers to the inputs. We refer to the outputs as the output layer, and everything else in between, these are called hidden layers. Now, the individual neurons over here operate on a set of inputs and produce a standard output. In the standard setup, the neuron first computes an affine function of the inputs. Again, recall that an affine function is a weighted sum of the inputs plus a bias. That is the z value in the figure over here. Then we apply a continuous activation function, f of z, to this affine value. And so this is going to be our standard neuron. Now, more generally, you don't need to have this kind of structure. A neuron can be any continuous differentiable function of its inputs. And we will see at least one case of such a neuron later, but unless otherwise specified, we are going to assume this form of neuron, where we have a continuous activation function applied to an affine function of the inputs. So the parameters of the neuron are the weights and the bias, and the parameters of the network are the weights and biases of all of the neurons in the network. Now, let's consider this activation function itself. Here are a number of popular activation functions that we could use and their derivatives. Historically, the most popular activation function was the sigmoid, which has the shape and form given in this top here. The equation is simply 1 over 1 plus e raised to minus z. F of z is 1 over 1 plus e raised to minus z. And it goes smoothly from being 0 for large negative numbers to becoming 1 for large positive numbers. The equation for the derivative is simply f of z times 1 minus f of z. I'm not going to derive it. It's very trivial to derive it from this formula. Now, this derivative, if you look at the derivative for the sigmoid, the derivative of the sigmoid is going to go from, this is the sigmoid, it goes from 0 to 1, right? And the derivative is going to be 0 out here, it's going to be 0 out here, and the derivative is going to go increase like so. It's going to be largest over here, and it's going to go back down here. And at this point, the slope is 0.25. So that is your sigmoid. Now, another popular activation function is the tanh. The tanh is simply the sigmoid, which is shifted and scaled so that it goes from -1 to 1. And the derivative of the tanh is given over here. The f prime z is 1 minus f squared of z. And the derivative of the tan h2 looks just like this, except that at this point, the slope is going to be 1. So this is one of the reasons why many people often prefer a tan h to the sigmoid, because in general, we like the maximum derivative of these activations to be as close to 1 as possible. This red curve here is the rectified linear unit. This is also very popular. Now the output equals the input when it's positive, and it's 0 when the input is negative. And at z equals 0, so that's the value is 0. But then the derivative of this function, in the negative regions, it's going to be 0. In the positive regions, it's going to be 1. And at z equals 0, there is no derivative, but you can, technically, but you can assume any value between 0 and 1. This will be what is called a subderivative. We're going to discuss subderivatives in more detail later in the lecture slides, maybe in the next class. So, and this blue curve over here, that is this guy here, that's just a smoother version of the ReLU, which actually has derivatives everywhere. So it becomes 0 over here. Beyond a point, it has a slope of 1. And the derivative goes from 0 and smoothly goes up to becoming 1. So the derivative of the soft plus ends up looking like a sigmoid. You're going to encounter other such activations during the course. Now, so far, we've assumed that a neuron takes in, a neuron takes in one input. This activation function takes in one input and produces one output. But then you can also have neurons which take in their inputs and produce multiple outputs. This is what we will call a scalar activation, where it takes in inputs but produces an output scalar. Instead, if it produces multiple outputs, I'm going to call it a vector activation. That's sort of illustrated by this pink box here. You have a single input which takes in a single unit, which takes in a bunch of inputs and produces a whole bunch of outputs. Now, this too will have many parameters, but then there's a fundamental difference between that and this. Here, if I change any one parameter, only one output is going to change. Whereas here, if I change, say, a parameter of an edge coming in here, all of the outputs will change. So in this case, a better notation than saying y equals f of x is to say the collection of outputs y is a function of the collection of inputs. So this is a vector activation. And a very common example of a vector activation is the softmax activation. A softmax that computes L outputs first takes in a bunch of inputs, then it computes L different affine terms. Those are the ZLs over here. And then to compute the actual outputs, each one of these, so you get L different affine values. Each one of these affine values is exponentiated, and then you normalize all of these exponentiated values so that they sum to 1. Now, because all of these outputs now sum to 1, you can think of them as a probability distribution. And the parameters of the softmax are the weights and biases of all of these affine terms. Now, see what happens. If I change the weight of this connection to increase this one affine term, because of this exponentiation, this is going to end up changing the corresponding output. But at the same time, because all of them must sum to 1, this results in all of these other guys decreasing, meaning changing any one parameter is going to change all of the outputs. So this is a nature of a vector activation. Now, to answer one of the questions on chat, you could, in principle, yeah, Gladys, what's the question?
May I ask for the previous slide?
Yeah.
What do you mean all of them must sum to 1?
Yes. Look at this over here, right? So I have several y's, right? This should have been yi, okay. And so I have, oh, come on, I have Z1 through say ZL, okay? Then I'm going to say e raised to Zi yi equals e raised to Zi divided by summation I e raised to Zi, right? So yi is always going to be positive because exponentiation results in positive numbers. Also, summation yi is simply going to give you summation e raised to I divided by summation e raised to I, which is equal to 1. Did I answer your question?
Oh, what is the thing you wrote on the right side?
So this is a 1. My scribbles are bad. This is e
Oh.
raised to I. And this is e raised to I.
Okay.
I'm using a different tablet today, so I'm having difficulty writing, but this is summation. This should have been, let me see if I can erase this. This should have been summation I yi equals summation I e raised to I divided by summation I e raised to I, right? Or summation j e raised to j, because this is how you define yi. So when you sum all of the yi's, the sum is going to be 1.
Okay.
Does it make sense?
Yeah.
Okay. So that
Big Shot,
means,
there's one question on the chat.
yeah, what is that?
The student is asking, can we say hidden layer is a single function that has multiple input and a multiple output?
You're predicting my next slide. You could, in principle, simply consider all the neurons in a layer as just being a single vector activation. From an outside perspective, if I just box up all of these neurons, and I claim that it's a single unit that takes in many inputs and produces many outputs, it satisfies the criterion to be a vector activation. And in fact, this would be a correct interpretation, although this is a special case where changing a single parameter, a single weight, only changes one output and not the one output and not the remaining outputs. And if I use this interpretation, in fact, every layer in the network is a vector activation, where for some layers, changing a weight will only affect one output. For others, typically for the final layer where we like to use softmaxes, changing one parameter is going to change all the outputs. Did that answer your question, Sam? Was it Sam? Okay. So I have defined F. And let's go ahead and define what these input-output pairs are. In defining a inputs and outputs, there are 3 things to consider: the input, the actual output of the network, and the desired output of the network. These are 3 different things. Now, so for us, the input is a vector, which I'm going to represent as x. The desired output in response to any vector input is also a vector with as many components as the output of the network, that I'm going to represent as d. The actual output of the network I'm going to represent as y. So I'm assuming that this is a network with a vector input and multiple outputs, which can be represented as a vector. This subscript n over here represents the nth training instance. I'm going to drop it. So I'll just focus on one training instance just for convenience. Okay. So consider the input. Any input to the network is a vector of numbers. Now, what these numbers are depends on the type of input. For images, these could be pixel values. If you're processing speech, this could be a vector of speech features. For text, this must be a vector of real numbers that somehow represent the text. How we get real numbers from text, we'll discuss later in the course. So regardless of the kind of input, eventually the input is going to be a vector of numbers derived from the input. So that's easy. The representation of the output depends on the nature of the problem. If you're trying to compute real valued outputs, then the outputs must be real valued. If the desired output is a scalar number instead of a vector of numbers, like in a scalar regression, then the network is going to have only one output with a real valued output, with a real one output neuron with a real valued output, and the desired output is also going to be a real valued number. If the desired output is a real valued vector, then your network is going to have the output layer of the neuron, the network is going to have as many outputs as the number of components in your desired value, in the desired output. And these outputs are also going to be real valued. So in the case of making real valued predictions, this is very easy. If the desired output is binary, like in a classification task, for instance, if I'm trying to classify images of cats, then what I would do is to say, I will convert this task, this task of deciding whether it's a cat or not a cat, to a numeric form. So now, whenever the network encounters an image of a cat, you want the network to output a 1. If it encounters something that's not a cat, this is going to, you want the network to output a 0. So the desired output now is going to have a simple 1-0 form. The actual output of the network is going to be typically a sigmoid of this kind. And the actual output of the network can be viewed as the probability of 1 given the input. This is a probability. So, if you're producing cat, showing it images, this is the probability that the image is that of a cat given that particular input itself. And so not only is this a probability, it's also differentiable. So it's kind of nice. So for simple single binary outputs, things are simple. If you have multi-class outputs for networks that perform multi-class classification, that classify inputs into more than one class. For example, a network that must distinguish if an input is a cat, a dog, a camel, a hat, or a flower, then we need a slightly more complex representation of the output. So if there are n classes, we are first going to construct an n component vector where each of the components represents one of the classes. So in our example, we're going to list our 5 classes: cat, dog, camel, hat, and flower in a chosen order in this vector. Then an instance of each class becomes a binary vector where all components are 0 except for one component. And that one component is the component corresponding to the target class. So for example, if I want to represent the class cat comes first in my list. So I will, and of course, I have 5 classes. So I will represent cat with a vector which is 5 components. It's going to have a 1 in the position corresponding to cat and 0 elsewhere. If I want to represent dog, it's going to be a 5-component vector with zeros with a 1 in the position of dog and zeros elsewhere. Similarly, for camel, the 1 is going to be in the 3rd position. The rest will be zeros. For hat, it's going to be in the 4th. For flower, it's going to be in the 5th. So in every case, there is only a single value, which is 1. The rest are 0. So because only one value is hot and the rest are cold, this is often called a one-hot representation or a one-hot vector. So for a multi-class classifier with n classes, the desired output is going to be an n component in response to every input. The desired output in response to every training input, which is going to belong to one of these classes, the desired output is going to be a one-hot vector corresponding to that class. So if you had a training instance, which is a picture of a cat, the desired output is going to be this one-hot vector with a 1 in the first position and 0 elsewhere. And so the neural network's output must also ideally be binary with n-1 zeros, and it must be a binary vector with n-1 zeros and a single 1. In reality, what we will have is a probability vector. We're going to use a softmax activation, and you're going to have many outputs whose values sum to 1. And so for multi-class classification, we will use a softmax vector activation We've seen this formula for the vector, for the softmax. And the ith output can be viewed as the probability of the ith class given the input. So if I had this example of, cat, dog, camel, hat, flower, then the first output is the probability that the input is an image of a cat. The second output is the probability that the input is an image of a dog, and so on. So this vector represents the uh, probabilities of the classes. And so with the inputs and desired outputs defined, here is a typical problem statement. We're going to be given a number of training instances, for example, images of digits along with information about which digit the image represents. In a binary classification task, the information could be simply, is this the number 2 or not? For a multi-class classification task, it could be this is the number 5, this is the number 0, this is the number 4. And we are working with discrete sets, countable sets. To get to infinite classes is a problem that we'll get to much later. But pretty much all the neural networks that you encounter in the world today are working with finite or at least countable sets. Now, so if I'm performing binary classification, say to recognize the digit 2, then we'd be given all these pictures, and against each digit you'd be given a binary label, is it 2 or not? So this is a 2, this is not a 2, and so on. And you're going to learn all the weights from this training. If you have a multi-class class, and of course, the network is going to have a single output, which outputs a probability of the class, and it should ideally be 1 for these guys and 1 for these 3 guys and 0 for the rest. If you have a multi-class classification problem, then you're going to be given these images of digits and the corresponding label. And then the network's output is going to be, in this case, a softmax with a 10 component output. And we learn the network parameters to minimize the error between the softmax output and the given labels, which will be represented, of course, as one-hot vectors when you actually learn the network. And so we've defined the inputs, we've defined the function, this function. There's one more thing left to define, which is this divergence. Now, which quantifies the error between the actual and desired outputs. Now, there's something very important to note. We want to minimize the loss with respect to the parameter W using gradient descent. That means we want all the components of this loss. We want this loss function. We want to be able to compute the derivatives or the gradient of this loss. To be able to compute the gradient of this loss, all components of the loss function must be differentiable. That means this network F must be differentiable, but then the divergence D must also be differentiable, otherwise the loss will not be differentiable. So this is a very important property of the divergence function. Now, when the desired output is a real valued vector, like in a regression problem, then there's a natural choice for the divergence function, which is the L2 divergence. This is simply the half of the squared Euclidean distance between the output vector of the network and the target vector that you want to compute, which is half of the sum over all of the components of the squared difference between the corresponding components of y and d. Now, here, when I write this divergence down, this y is actually a function of the input and the parameters. The desired output, again, is a function of the input. It's specific to the input. I'm just not showing these explicit dependencies. Now, what is this half doing over here? It's just a matter of convenience. Now, observe that the divergence is a scalar number. It's a real valued number which quantifies the difference between the desired and actual outputs. The divergence is always a scalar. And so when I differentiate this divergence with respect to the various outputs of the network, when I use an L2 divergence, this is a squared term. When I differentiate it, I get a multiplicative factor of 2 coming out. That's going to cancel the 2. And that's the only reason we have this 2. It's a matter of convenience. It gets rid of the 2 that comes up from the differentiation. And so when I take the derivative of this divergence with respect to, say, any one component of the output, yi, that is simply going to be the derivative, the 2's will cancel out. We're just going to end up with yi minus di. So which is the difference between the actual output and the desired output. And so the gradient, the derivative of the divergence with respect to this entire vector y, output vector y, is going to be a row vector of the partial derivatives with respect to the individual components. And each of these partial derivatives is simply, because of the manner in which we've defined this, the difference between the actual output and the desired output. So this is the error. This is the actual error. And so the derivative of the divergence with respect to the output vector y is going to be a vector of the error between the actual output and the desired output. It's a vector of errors for the L2 divergence. This is for the case where we are trying to perform real valued predictions, when the network is computing something real valued. For binary classification, we have a much more popular divergence. This is the Kullback-Leibler divergence. Now, for binary classification, remember the desired output is going to be either 0 or 1. And the network output, we said we were going to use a sigmoid activation. So the network output is going to be a value between 0 and 1. Now, I can think of this binary output, so I have D belongs to 0 or 1, right? It's either 0 or 1. So when I have so let's say I'm trying to perform, I'm trying to recognize the digit 2. I can give it an image of the digit 2, and my desired output is going to be 1. I can think of this as saying that the probability of 2 for this image is 1, and the probability of not 2 is 0. Similarly, I can, if somebody gives me a picture of 3, this is not the digit 2, so my D is going to be 0. So this is like saying that the probability of 2 given this picture of 3 is 0, and the probability of not 2 given the same input is 1. So you can literally think of this desired output as a probability, but it's not just any odd probability, it's a probability with certainty. And the actual output of the network is the probability estimated by the network. And so I can think of the ideal output as this vector D, 1 minus D. For instances from the target class, this becomes 1, 0. For instances from the other class, something that is not the target class, then D is going to be 0, and then 1 minus D is going to become 1. So this is going to be 0, 1. And now the Kullback-Leibler, so I have at this point, the target output has been mapped on to this vector, which is D and 1 minus D. 1 minus D. The output of the network can similarly be mapped onto this vector y, 1 minus y. This is the probability that the estimated probability that the input belongs to the target class. This is the estimated probability that it does not belong to the target class. And when you define things this way, then the Kullback-Leibler divergence, KL between D and Y, is going to be what we have on the slide over here. It's going to be minus D log Y minus 1 minus D log 1 minus Y. Now, look at what happens over here. So I'm writing this as minus of d log y minus 1 minus d log 1 minus 1, right? So if I'm trying to build a classifier for the digit 2, and the training instance is actually an instance of 2, then what is d going to be? Anyone? What's d going to be? It's
1.
going to be 1. So what will the callback library divergence become? This becomes 0. So this is simply going to become minus d log y, correct? And on the other hand, suppose I give you this one, an input which is a 3. What is d?
0.
This 0, right? So this term disappears, and your callback library divergence is going to be, and actually because d is 1, this simply becomes minus log y, correct? In this case, 1 minus d is 1. So this is simply going to become minus log 1 minus 1. Now, if the network is outputting the correct value for the input, then y is going to be equal to d, right? So for this image, what is the ideal output of the network for y?
1,
Then what does this become?
0,
For this image, what is the ideal output?
0,
So this becomes
0.
0 also. So the divergence becomes 0 when y equals d, right? And when y doesn't equal d, what is the range of y? It's between
1.
0
0
and 1, 0 to 1. So what will the sign of this log y be?
will go to 0 to infinity, I guess.
Minus infinities. Log y is going to be negative, right?
But there is a minus sign here.
So once you factor in the minus, it becomes positive. And so this callback library divergence is guaranteed to be positive when d is not equal to y and 0 when d equals y. And moreover, when you take a derivative, right? If I take the derivative of this callback library divergence with respect to y, for an instance from the target class, the divergence becomes simply minus log y. So the derivative, divergence over y is simply going to be minus 1 over y, right? In this case, the derivative d divergence over dy is going to be 1 over 1 minus 1. It's just the derivative of this term. You guys see how these two go together, right? So from this one, you got this derivative. When you got a training instance from the target class, when you got a training instance from some other class, you got this one. Yeah. And so you get this derivative for the callback library divergence. Now, here is something very interesting. What is the derivative when the network is doing the correct thing? So let's say I give it an image 2, and the network correctly assigns a probability of exactly 1 to the input. What is the derivative of the divergence with respect to y? It's minus 1, right? What about when I give you an instance where the derivative is or an instance of 3 and the network does the correct thing? What is the derivative?
1 again.
It's going to be 1, right? So here's the situation thing. Even at the minimum, the derivative is not 0. I've been fooling you all along saying that, you have these functions and that at the minimum, the derivative is going to be 0, correct? That's not required. The derivative may not be 0. And also, I can ask the question, why do I need a callback library divergence? I mean, I could pretty well have just used the L2 divergence and that works too, right? Why KL and not L2? And the answer lies here. To see how KL and L2 divergences behave, consider these two plots. Over here, the desired output is 0. Here, the desired output is 1. Now, the red curve is the L2 divergence between the desired output and the actual output. The blue curve is the Kullback-Leibler divergence between the desired output and the actual output. Now, the L2 divergence is a nice, beautiful goal, but it's ignoring the fact that this is a classification problem. So if the desired output is 0, if it's not a cat and the network is 100% confident that if it's not a digit 2, and if the network is 100% confident that it's a digit 2. So, wait a minute, give me a second. Then it's infinitely wrong, right? Because when it's 2 and it's saying, oh, when it's not 2 and it's saying it is a 2, it's infinitely wrong. So also when it's 2 and it's 100% confident that it's not a 2, it's infinitely wrong. That's something that the L2 divergence completely ignores. The Kullback-Leibler divergence actually gives you this very nice behavior that it actually shows you the kind of behavior you would like. When something is 100% certain of the wrong thing, it is infinitely bad. And the L2 divergence sort of loses this feature. But then in exchange, the L2 divergence has zero gradient at the correct answer, whereas the KL divergence, for d equals 0, you get the slope of 1. For d equals 1, you get a slope of -1 at the minimum. So this is, and so for here is the derivative of the KL divergence with respect to y. And when d is 1, it's going to be -1 over y. When d is 0, it's going to be 1 over 1 minus y. Note that when y equals d, the derivative is not 0, even though the divergence is 0. I have one last poll, which is, let's see if I have time for this. I may run a few minutes over, but you get 30 seconds. Ten seconds, guys. Hurry up. All right, let me stop this. So the gradient of the loss may be 0 or close to 0 at the minimum, like in the L2 case, but the gradient of the loss may actually have a large magnitude even at the minimum, as we saw for the KL divergence. Both of these are feasible. The other two are wrong answers. Now, I'm going to go maybe 2 minutes over, so just bear with me, guys. Let's go to the multi-class case. For multi-class classification, the desired output D is going to be a one-hot vector. The network output is a vector of probabilities. This is also going to sum to 1. Even in this case, I'm going to use the Kullback-Leibler divergence. And in this case, the Kullback-Leibler divergence is defined, you have a multi-component vector. So the Kullback-Leibler divergence is going to be sum over, this divergence D is going to be the sum over all components of di times log of di over yi, which is the output of the network, which is d1 log d1 over y1 plus d2 log d2 over y2, and so on. Okay, remember, this is a one-hot vector. Now, suppose I have a training instance which belongs to class 3. What is this divergence going to be if I simplify it? Anyone?
Log
What's
1
it going to be? It's going to be what?
log 1 by y3.
Log of 1 over y3. That's it, right? Which is minus log y3. And what is the derivative of this divergence with respect to, say, y1? What is it?
0.
0. What about with respect to y3?
-1 by y3.
minus 1 by y3. So you can see how this works, right? So the for one hot vectors, all the d's from the non-target class are 0, and only for the target class d is 1. So this simply becomes minus log of the y for the target class. And the derivative of this divergence is going to be minus 1 over y for the target class and 0 for everything else. So if I actually write out the derivative vector, it's going to be a vector of zeros, except for the target class where it's going to be minus 1 over y. Now observe something very interesting. This derivative only has a component for the target class. Now, if the network is assigning a low probability to the target class, what is the derivative going to be like? Is it going to be a large negative value, a large positive value, a small negative value, or a small positive value?
Large negative value.
It's going to be a large negative value. So when the network is assigning a low probability to the target class, it's going to ask you to take a big step backwards, right? If the network is assigning a large probability, then it's going to ask you to take a small step backwards. So it has this nice property that it's always trying to increase the probability of the target class. And the smaller this probability is naturally, the more it's going to try to increase it. And also, once again, observe that when the network is doing the correct job, when y equals d, the slope is minus 1 over here. So even though the divergence is 0, the slope is minus 1. And so we have sort of defined all of the terms in this loss. All we have to worry about is how to minimize it. And so the story so far, neural networks are trained to approximate functions by adjusting their parameters to minimize the average divergence between the actual output and desired output at a set of training instances. To train them, we must define several things: the network, the manner in which the input is represented, the manner in which the outputs are represented, and the divergence function that computes the error between the actual and desired outputs, which is the L2 divergence for real valued predictions and KL divergence for classifiers. And once you define all of that, we are set to perform compute derivatives and perform gradient descent to train the network. So I'll stop right here. And if you have any questions, I can take them for the next few minutes. Also, you can post questions on Piazza. Questions, anyone?
Can I ask a question? Like, could you go back to the multi-class output, that slide? Yeah, exactly. So could you explain a little bit, like, in the red box on the top, there's there's yi and also di. So I kind of like confuse the two terms.
So
like,
this is the actual output of the network, these four.
Right.
So and this is the desired output of the network. So for example, if I'm saying, let's say I'm trying to classify between, say, cat, dog, horse, and maybe elephant, right? Then I give you a picture of a cat. Then this, what is the target output in this case?
1000.
1000, correct? So this guy over here is the desired output. It's going to be 1000. And this is the output of the network. Ideally, you also want that to be 1000, but it might be anything, right?
Right.
And so the divergence between those two is given by this formula over here, which just ends up, as we saw, being minus of the log of the probability assigned to cat by the network.
Right. And by the way, like all the yi sum up to 1, right?
Yes, because this is a softmax.
All right. There is no question.
So this is a probability, right? It's always outputting a probability. Yeah. Any other questions, folks?
I have a question.
The student is asking the difference between validation set and test set.
We haven't gotten anywhere close to that, right? Your validation and test set are a concept entirely different from training, but this is a validation set is a data set that you use to predict your network's performance on the test set. It's some data that has not been used in training, but which you have access to, where you know the ground truth. So you can actually compute the network's output on this validation set, compute the error, and take a guess as to what the error is going to be in the real world. The test set is the real world. Yes, the network output is a softmax. So this is going to be a softmax output, right? You want the Y's to be a probability set of probabilities. So you will be using the softmax. So Hassan, you're sort of jumping the gun over here. We'll get to that in a few classes. Any other questions?
Yeah, I had a question about the KL divergence loss.
Yeah.
If even at the minimum, the gradient of the divergence is not zero, wouldn't that mean for using gradient descent, we have something like unbounded growth of the weights? If we're not careful about eta.
So that's actually a good question, right? The point is this: you're going to be testing the loss. So if you're at the correct answer, then the convergence criterion is going to stop you.
Right,
because
it would be the criterion would be the one
not,
there's not much change between the loss function.
Yes, exactly.
Got it. Thank you.
Right. Our loss function should be smooth. You can there is a lot you end up well. There are many problems where a smooth loss function is not natural. I mean, a smooth error function is not natural, and so in those cases, you have to sort of approximate it with a smooth differentiable function. There's a certain amount of work on that, but you
this question was
eventually need a
particularly
differentiable
with
function.
This question was particularly with the dice loss, because dice loss is generally not a smooth function, right?
But to minimize it, eventually you're going to have to come up with
approximate it to like some kind of a softer version of dice loss.
That is differentiable. You cannot, if you don't have a differentiable function, or if the derivative is always zero. This is what we saw in the last class. You don't know which way to move your parameters.
Right. Okay. Understood.
Right.
Yeah. Thank you.
I have a question regarding KL divergence.
Yeah.
So it looks like the slide in slides 84 and 85, the formula for KL divergence is different.
In slide 84, it is this is 84 di log di, which becomes minus yc, and
yes, so 85 you only have the second term, and the first term is missing.
Okay, so this is a bug. I'll have to fix it. Can you post it on Piazza? I'll fix it. Good catch. It should have been this. It should have been this. Okay, you cannot ignore this term. For one hot representations, you can ignore it because di log di is always going to be zero. Either log di is going to be zero or di is going to be zero. So this is correct for one hot representations. But there is a slide on label smoothing where this formula would be wrong.
Actually, I wonder, so if di is zero, then log di would be minus infinity, right?
But so the point is log increases much slower. It's sublinear. Okay, so 0 log 0 is 0 because log compresses. If you look at it this way, if I plot it, right? If I plot it, this is say x, and then if I plot this is going to be y equals x, and this is going to be y equals log x, right? So this guy always increases faster than this guy. This will dominate.
Sorry, what's the error you said that's on the slide again?
This one, see this formula? It's di log di over yi. This is just di log yi. It should have been, there's this first term that's missing. I forgot to write it.
So for the multi-class Oh, okay, I see.
right? Yeah, that's a mistake. Okay. Any other questions, guys?
Professor, I have a question about KL divergence in
Yeah.
slide 84. And
Just hang on, I'm going to stop recording and then I'll continue. Okay.